Hi, and welcome to Failurology, a podcast about engineering failures. I'm your host, Nicole, and I'm from Calgary, Alberta. And joining me again this week is Brian. Welcome, Brian.
Thanks for having me again. I had so much fun being part of the Comet episode.
So much fun that you came back for more?
At least one more.
At least. I'm glad I didn't scare you away. This episode's engineering news is about the Champlain Towers. We touched on them at the last episode, but the last episode came out not too long after the collapse. So there are more things that have happened. We wanted to touch on that again, just provide an update. This is a really tragic, but also technically interesting failure that is relevant to this podcast that we wanted to talk about. I'm just going to recap some of the information that we talked about last time. So on June 24th at around 1:25 a.m. Eastern Time, a large section of the South Champlain Towers collapsed. As of this recording, the death toll is up to 97. There are 11 people with non-fatal injuries, and there are still 8 people missing. The building was completed construction in 1981. It stood 48 meters tall, or 12 floors, and it had 136 units. The uncollapsed portion, so only, I would say, a third to half of the South Tower collapsed, but the piece that was still standing has since been demolished. That happened on July 4th. The building's located in Surfside, Florida, which is just north of Miami Beach. And one thing that I thought was interesting, so there's 3 towers in this complex. There's a North and South Tower, both built in 1981. And then there's another tower in the middle. All of them are 12 stories. I have not heard about what's happening to the other 2 towers. I assume they're being investigated. A group of engineers have reviewed a lot of the footage. There was a lot of surveillance footage from nearby buildings that people were able to review and try to figure out what happened. And from what it looks like on those videos, a large north central section of the building collapsed first, which isolated and destabilized the northeast corner, which then also collapsed 9 seconds later. So this total collapse took place over 12 seconds.
Does the city of Surfside require inspections or audits on buildings over a certain age or height, or for high-rise towers or other structures?
I don't know, because I've never done work in Florida, but I will say that I did read, I think there's a 40-year inspection that needs to take place. And if I'm remembering this correctly, they were in the process of completing that inspection when the building collapsed. So that's really unfortunate. And then the building residents had undertaken some of their own inspections. They'd hired a structural engineering firm to do a report on the building to audit the structure. And then, of course, there's been, every time there's a renovation or any significant work done within a unit or on site, there's permits pulled from the city, and those permits obviously come along with inspections. So there have been inspections at the building, but from what I've read, most of those inspections were related to plumbing or electrical and not specifically tied to the structure.
Yeah, that's really unfortunate that it sounds like they had things in place, they were going through some structural inspections, and then the collapse happened.
Yeah, I'm going to get into that actually. On June 26th, the mayor ordered an audit of all high-rise buildings over 40 years old, as well as all buildings by that same developer who built Champlain. And this was to take place over 30 days. So this will be done by the end of July. Crestview Towers in North Miami Beach was closed and evacuated due to structural and electrical concerns on July 2nd. And the Miami-Dade County Courthouse was closed on July 9th due to safety concerns. And there have been others as well. So as tragic as this is, it seems to have jump-started a reaction where people are looking at their structure and actually making safety calls over whether or not the building should be occupied, which silver lining is a good thing. I mean, it shouldn't have to take this type of incident for that to happen, but at least it's happening.
We've seen that a lot too in other episodes that we've looked at, where there's been a significant incident that happens that spurs on further proactive or corrective actions. So sometimes it does take a fairly significant incident to institute or start change.
Yes, which is very frustrating that something so significant and tragic has to happen before people pay attention. KCE Structural Engineers was engaged on June 27th to study and assess the collapse. They were involved in assessing the Pentagon after 9/11 and the Florida International University pedestrian bridge collapse in 2018. There's a lot of people weighing in on what happened here at Champlain. And so There's kind of a list of possible causes, and I'm just going to kind of give an overview of those right now. So as we talked about in the last episode, there was a 2018 structural inspection report which called out sloping errors in the waterproofing layer of the pool deck. So what that meant was that the waterproofing layer was flat, there was no slope to it, so water would sit on it until it evaporated, which significantly decreased the lifespan of the membrane, which in turn, if the membrane is not repaired, decreases the lifespan of the concrete that it's protecting. The report stated, quote, failure to replace waterproofing in the near future will cause the extent of the concrete deterioration to expand exponentially, end quote. Pretty significant repairs were needed to address this waterproofing that had failed. I mean, the waterproofing was almost 40 years old at that point when this report was done. I think it would have been 37 years old. So it's not unreasonable that it needs to be replaced. But if you'll remember from the last episode, the waterproofing was underneath a concrete topping. And so it's not as simple as just tearing up the membrane and putting a new one down. They had to tear up that concrete topping, then tear up the membrane, then put a new one down, assuming there were no structural repairs to the concrete underneath it. So it was a significant cost and time scope, and it would have been a really big disruption to all of the residents. So I mean, hindsight's 2020. I'm not really surprised they didn't act immediately because it's a big undertaking.
It does sound like a fairly involved project to replace the membrane or even do an inspection of the concrete underneath the membrane.
Yeah. In October 2020, the repairs hadn't been completed because the deterioration of the concrete was so bad that any repairs risk destabilizing the area. So the building was taking steps to try to fix it, but they just hadn't gotten very far. On April 9th of this year, residents received a letter outlining a $15 million remedial works program, which is huge. Part of this was roof works, which were underway when it collapsed, but the concrete work hadn't started. So assuming there was no money in the reserve fund, which may or may not have been the case, I definitely don't know the answer to that. But if you just look at $15 million by 136 units, that's a $110,000 special assessment per unit, which I don't know about you, Brian, but I don't have 110,000 lying around.
I don't have 110,000 lying around.
A pool contractor had been on site about 36 hours before the collapse, and they shared photos of the pool equipment room, which is underground in the underground parking, and there was significant infiltration of salt water, resulting in more spalling and corroded exposed rebar. 7 minutes before the collapse, which is insane, a bystander recorded video of water pouring in from the parkade from above near the entrance door. So the video is taken from out on the street looking in. This is Florida. They don't have winter, which is a weird concept to me. So the parkade door is just a gate, just a wrought iron bar gate. And the video is looking inside the entry door of the parkade, and you can see concrete lying on the ground and water pouring in. The New York Times reported that investigators found less rebar in the footing and columns than specified on the drawings. It is possible that the requirements for rebar were changed during construction with oversight from the engineer. That kind of stuff does happen. It's not impossible, but it's also entirely possible that the contractor cut corners and no one caught it. And that's something we don't know yet. We'll find that out once they finish the investigation. Another possible cause, so data from the Florida International University indicates that the building's been sinking at a rate of 2 millimeters per year, while 97% of Miami Beach has been stable. Subsidence is a real big problem in places like Florida and New Orleans. You know, I did the levees in New Orleans during Hurricane Katrina in episode 2, which was very early on. But New Orleans is sinking at a quite substantial rate. When New Orleans was first developed, it wasn't below sea level like it is today. It's a real big problem. That said, that is likely only a cause of this building collapse if one part of the building was sinking faster than the other. If the whole building was sinking at the same rate, that wouldn't really have impacted one part falling down over the other. And then lastly, I just want to say that based on a consensus of 6 engineering reports, the Miami Herald reported that based on publicly available evidence, which, if I must say, is a lot of information. There's a lot that's been released, which makes me happy because normally there's not very much. Normally everyone keeps it pretty tight-lipped. Anyways, experts believe that a column or slab underneath the pool deck gave way first, causing the pool to collapse into the garage, which destabilized the tower and then causing that to collapse. And I also wanted to add, because I thought this was interesting, speaking of a lot of information being out about this failure, information for this engineering news segment came from Wikipedia, They have 176 resources linked to this one topic alone, which in itself is really, really impressive. Wikipedia is usually the first place that I start when I'm researching, and I usually look through the sources to see if there's any more reports that I can pull. They usually have links there. 176 is huge. Normally there's definitely less than 100, probably maybe around 30 to 50, depending on the failure. There's a lot of information, and we're really just getting started. I mean, this happened less than a month ago. So I'm sure there's still going to be a lot more information to come out, especially once that report comes out. What do you think, Brian?
I do think this will be interesting to follow over the next number of months or number of years as the investigation runs its course, and likely there will be additional lawsuits that come out of this.
Yeah, it's very interesting. Extremely tragic. I mean, this happened at 1:30 in the morning. People are sleeping.
And it happened over a 12-second period of time, so it's not like there were indications for weeks or months that were visible to the residents. It's all of a sudden, over 12 seconds, the buildings collapsed.
Yeah, although I disagree, there was definitely evidence to suggest this would happen. Although, I mean, people don't think that the whole building's going to fall down. So I'm not blaming individual residents for sure.
But as a resident or somebody that lives in the building, they likely wouldn't be aware of issues that were present in the building just by visually being able to look at something. And at some point, we place a lot of trust in engineers and architects and building designers and building codes to ensure that things are safe and people are able to live and work in large high-rise structures.
Right. Yeah. Yeah, agreed. Okay, if you want to read more on the Champlain Tower collapse, check out the link in the show notes or head to failurology.ca. You can also look it up on Wikipedia or, I mean, really at this point, just simply Google Champlain Tower collapse and you will find tons and tons of articles. This week's episode of Failurology is brought to you by Long's Long Pants.
They're long pants made by Longs.
Not to be confused with shorts. These are different.
This seems pretty self-explanatory from the name.
But yet, here we are, explaining long pants.
Long's long pants. Now, on to this week's engineering failure. The floating bridges of Washington State, which sank. Not one bridge sank, but two. One bridge sinking isn't something that should happen. Two is definitely not something that should happen. So, what is a floating bridge? Floating bridges are made of large watertight pontoons connected rigidly end to end upon which the roadway is built. Despite their heavy concrete composition, the weight of the water displaced by the pontoons is equal to the weight of the structure, including all the traffic that goes across the bridge, which allows the bridge to float. So here in Canada, in Kelowna, the William R. Bennett Bridge that connects downtown Kelowna to West Kelowna is the 9th longest pontoon bridge in the world at 690 meters.
Did you know that was a floating bridge?
I had no idea it was a floating bridge until I started researching for this episode. I've driven across it a number of times. I wondered why it was so close to the water. It had a unique design to it, but I never knew that it was a pontoon bridge. And now I found out that it's a pontoon bridge. And the 9th longest one in the world too.
Yeah, I've driven over it several times, and I probably was told at one point that it was a floating bridge, but when we started researching this, that I did not connect those dots until I found a list of the world's longest floating bridges, and then it was like a light bulb.
I also did not make that connection until I saw that it connected downtown Kelowna to West Kelowna. I just thought it was a neat bridge design that I hadn't seen before here in Alberta. So Washington State is actually the floating bridge capital of the world. They have 4 out of the 5 longest floating bridges, and the longest 4 pontoon bridges are located in North America. So just like me and Nicole, you may have driven across one in your life before.
I didn't know that about Washington State either, which is kind of a cool claim to fame.
4 of the 5 longest floating bridges. So there's either not a lot of floating bridges around the world, or Washington State just really likes their floating bridges.
Well, I don't think they're all that popular, it seems. Washington State must have a lot of really, really deep lakes and waterways, and that's where the pontoon bridges really thrive. So I'm assuming that's where that comes from. But yeah, it's not really that common, I don't think.
Yeah, so if anyone's listening in Washington State, let us know if you've driven across 4 of the 5 longest floating bridges in the world. We'd be interested to hear. Pontoon bridges were likely the first attempts that humans made to cross any sort of waterway. They were able to put something that floated across the river, and then they were able to walk across or put a platform over the top and go from one bank to the other. So it was very, very early form of bridge construction. And the first detailed record that we have, or at least that we could find, came from the 5th century BC. And that was for a bridge, or a bridge over top of boats that was used to cross the Hellespont by Persian King Xerxes in one of his military campaigns. So that was 2,500 years ago we came up with, or there was a detailed description of pontoon bridges.
Which is so interesting. It's almost like old technology that's still relevant.
But it still works for the most part, unless they sink.
Of course, yes, which we're going to get into. But first, there are some factors to consider when building a floating bridge. First and foremost, you have the floating elements, or the pontoons, which I'll say are the most important part of a floating bridge. If they don't work, the bridge doesn't work.
So Nicole, those pontoons, those are kind of like the outriggers on the bridge, right? They go out quite a ways from the bridge deck or the driving surface, just to provide some stability to the bridge.
So I've seen a couple different sections of various bridges. There's a bunch of different, I guess, configurations. So sometimes they have the pontoons are much wider than the bridge deck itself. But then there's also scenarios where the bridge deck is really, really wide. And so maybe the pontoons go 3/4 of the way, and then the rest of the bridge deck is cantilevered off the sides.
Interesting.
So the pontoons can be made of wood, steel, concrete, rubber, plastic. There's a ton of options. It really just needs to be strong enough. So it kind of depends on what your application is, what the longevity is. I don't recommend making a highway bridge out of plastic pontoons. That doesn't really seem like it's going to last for a long time. Concrete seems to be the most common in those applications. But I've seen lots of floating docks, for example, or floating bridges that are made for people that are made of plastic pontoons. The pontoons are typically made elsewhere, and then they're towed into place. And there's usually multiple pontoons grouped together. So it's not just a row of one pontoon down a chain. It's usually, the bridges we're talking about in Washington State are 5-6 pontoons wide in most cases. And then those are grouped together kind of as you go down the bridge deck. Which brings me to the next piece, the bridge deck. There are beams that go in place between the pontoons to support the deck, and then they place a metal mesh or a metal sheet on top of the pontoons to build the deck across. In the olden days, they used to use wood for that application. And because the bridge moves, it moves due to various factors, which I'm going to get into in a second. There has to be some flexibility between the sections, which I think is really important to think about because asphalt is not an overly flexible material. So I'm imagining that there's expansion joints or flex joints kind of throughout the length of the bridge, especially on those longer bridges.
Yeah, this sounds quite a bit like floating docks that people would have for their boats, I guess they anchor their boats, or they, walk along between their boats, right? They're floated on pontoons. There's, the sections are built, but there's some flexibility between the two sections.
Yeah.
With that in mind, I mean, how do these things get anchored?
So there's a few different ways to anchor them, and it seems as though most of the bridges use multiple different types of anchors. So a single bridge may use 2 or 3 different types of anchors, depending on what they're dealing with. The reason that they use these floating bridges typically is because the water that they're trying to cross is really, really deep, or the soil conditions at the bottom of the lake bed or whatever the waterway is are not ideal to support a bridge structure or a pier of some kind. And so that's where these floating bridges really shine. What they do is they put these anchors in place on either side of the bridge at the lake bed level, and then they run cables up to hold the bridge in place so that the bridge kind of can't really sway too far to either side because they've got cables that hold it in place. There are 3 common types of anchors. The first is a fluke anchor, which is similar to a traditional boat anchor. It looks like a flat plate with a wireframe pyramid, and then that sits in the ground, in the soil underneath the water, and then a cable runs up to the bridge. And these fluke anchors are best in deep water, soft soils, flat areas, and they usually can support up to about 1,000 tons of force.
So very similar to a boat anchor.
Very similar to a boat anchor, yeah. In reading this, I didn't know this, but the barbs, I'll call them, on a boat anchor, those are called flukes, which I didn't know that. Also, there's a lot of different types of anchors. That's a Google rabbit hole that you didn't know you needed to go down.
Does the fluke name come from the flukes on whale tails at all?
Oh, maybe. Oh, that's interesting.
Yeah, I believe they're similar shapes, right? They kind of have that shape of a whale tail.
I didn't know whale tails were called flukes.
I believe that's what they're called.
Fascinating. Biology's not my strong science.
Not mine either.
I prefer physics. The next type is a gravity anchor, which is basically just a really heavy weight that they put on the bottom of the lake bed and that the bridge is tethered to. It's ideal for solid soils, sloped topography, and it's ideal for locations near the shore. Those can support up to 500 or 600 tons. And then lastly, as far as the common types of floating bridge anchors is drilled shaft anchors, which they're very similar to gravity anchors. They're cylindrical, basically poles or piles that they drive into the ground so that only a portion of it sticks up. And then that portion that sticks up is secured to the floating bridge. The drilled shaft anchors are typically used in similar locations to gravity anchors, but in locations where a gravity anchor might be really hard to navigate around. Gravity anchors are really, really big and bulky. They're kind of like a Jersey barrier, but under the water. So you don't want to use those in places where other boats could hit them. So a drilled shaft anchor offers you an alternate solution that's very similar. And as I said, the Washington bridges and a lot of other floating bridges around the world use a combination of these different anchor types depending on the lake bed soil composition, depth, water traffic, etc. And a lot of them use multiple types. So some of the bridges that we're talking about today use the fluke anchors as well as the gravity anchor, and some of them use the drilled shaft anchors as well. So I don't think it's a one-size-fits-all solution. I think maybe closer to the shore, you use gravity or drilled shaft anchors. And then as you get into the deeper water, you swap out to the fluke anchors.
So just speaking of water traffic, how do ships actually get past these bridges since they're so close to the water?
So there's two common ways that I've seen. One is that the bridge retracts. So a section of the bridge basically tucks into itself and opens up a passageway in between those two sections, which, while that seems simple in concept, I'm not a fan of that idea. That doesn't seem like a great idea. I feel like you're kind of compromising the structural integrity of the bridge because you don't have a continuous span across the waterway. That's just me, though. I don't know that that's necessarily true, but it just doesn't. I don't know. I don't love that idea. Or the other concept that I've seen a lot is that a portion of the bridge is fixed. So your approaches, which we'll get to shortly, your on or off ramps to the bridge, a section of that can be fixed at a higher elevation so that ships can pass under that. And then the cars would, after they go over that fixed portion, then they would drive down closer to the water level and get on and enter onto the floating bridge from there. So the Kelowna Bridge that we talked about, the one that goes from downtown to West Kelowna, it has a fixed portion that allows boats to pass underneath. It looks kind of weird because the bridge has a big hump in the middle of it. And so you drive across, you drive up and over the hump and then back down onto the floating portion.
I had always wondered why that bridge had a weird shape to it. So thank you for letting me know why it has a weird shape to it.
It does look really weird. It makes sense when you think about it, but at first you're like, that bridge looks different. Some other important factors to consider are all the forces on the bridge. So you've got the weight of the bridge deck itself, which is the static load, and then you have a number of dynamic loads. You have traffic loads, so the weights and forces of all the vehicles driving across. You also have the drag force from the current, the water current, and waves. You have the reactions of the anchors. So as the waves are pushing the bridge one way, the anchors are pulling it back another way. And then you also have what is referred to as Archimedes' thrust, which says that if a solid body floats or is submerged in a liquid, the liquid exerts an upward thrust force, a buoyant force, on the body equal to the gravitational force on the liquid displaced by the body. So you've got these thrust forces that are placed on the underside of the bridge to keep it floating. There's a lot going on here that you have to account for. And I think one of the trickiest pieces is, especially in these high wind or high current areas or on these longer bridges, these busy bridges, the forces are never constant and they're never all the same. So you almost have to plan for the worst case scenario of each of these different forces, which probably means that your bridge is over-designed in some aspects, but not doing that could mean that it sinks, which we will get into shortly.
So some of these forces too would kind of compound on each other, kind of a crack the whip sort of thing, where one section to move, and that would compound and follow into the next section, and the force would be multiplied along the bridge. I would assume. Is that correct?
Yeah, I would assume so. Yeah, the bridge is kind of, I guess you could look at it like your spine. It's all, each of these are your different vertebrae, and they're all kind of connected together. And so any force that you exert on one is then going to be exerted to a certain degree on all the other sections. And the bridge kind of has that flexibility to it. Even though this is really old technology and it's really, it's been done before and it's been done lots, it does seem like it's a bit complicated to pull off in modern day applications where you have 6-8 lane highway with 24-hour traffic, travels 2 kilometers across a heavy current waterway. That's a lot of factors.
Yeah, because one end of the bridge could be subjected to completely different traffic or wind or wave loads than the other side of the bridge, and you need that whole bridge to remain in place so that none of the cars fall into the water.
Exactly. We don't want any cars to fall into the water. That's bad. Okay, and then lastly, we have the approaches. So these, like I said before, these are the ramps that are used to get on and off the bridge. Usually there's, for each, if we're looking at one ramp specifically, there's one fixed point and one rolling point. So in addition to all of the other forces that we talked about, the tide changes. So the bridge moves up and down. As the water level rises and lowers, the bridge moves, and those approaches, which are fixed, have to adjust for that movement.
Yes. So similar to a dock or a marina where the tide comes in and the tide goes out, or the water level in the lake changes with seasonality or with damming stuff. So yeah, it still needs to go up and down and needs some flexibility. The first floating bridge that we're going to talk about today is the Hood Canal Bridge. The Hood Canal Bridge is the third longest floating bridge in the world and the longest saltwater floating bridge in the world. The floating portion of the bridge is just under 2 kilometers long, and it's part of Route 104 across the Puget Sound and connects Olympia and the Kitsap Peninsula. The bridge cost $26.6 million in 1961 dollars. The bridge was opened in 1961 and is the second concrete floating bridge constructed in Washington. The first one, the Lacey V Murrow Bridge, we'll talk about in a second. So the pontoon bridge had a retractable drawspan so the boats could pass through, and the depth below the bridge was 25 to 105 meters with tidal swings of 5 meters. So it's a fairly deep water underneath the bridge, which is likely why they went with a floating pontoon bridge. Overnight, the bridge had sustained winds of 137 kilometers per hour and gusts of 190 kilometers per hour, which led to the bridge sinking at 7:30 in the morning on February the 13th. So overnight, the drawspan was open to relieve any lateral pressure, but unfortunately this led to the western half breaking loose and sinking. Blown open hatches allowed flooding of the pontoon. The bridge was reopened on October 24th, 1982 for a total cost of $143 million, with $100 million coming from federal emergency bridge replacement funds, and this remained a toll bridge until 1985.
Do you know if the Hood Canal Bridge was open when it sank?
The bridge was closed due to the high winds. There was no traffic that was going across the bridge at the time, which is probably a good thing, since if it had sunk with cars on it, this would be a lot more severe.
I like it when no one gets hurt. Those are the kinds of failures I like to read about.
And if something's going to fail, it's probably best if there's not any lives that come along with the failure.
Yes. So the next bridge we're going to talk about is the Lacey V Murrow Bridge, which is the second longest floating bridge in the world at just over 2,000 meters. It's part of Interstate 90 across Lake Washington and connects Seattle to Mercer Island. It originally opened in 1940 and was named Lake Washington Floating Bridge, but they renamed it Lacey V Murrow in 1967.
I feel like the Lake Washington Floating Bridge is a much more descriptive name.
Yeah, I would agree. I don't know what they still call it. I wonder if the locals still call it the Lake Washington Floating Bridge. I'd imagine that they call it Murrow Bridge because that's probably a lot faster to say. So the original bridge closed in 1989 for major repair work with the intention of being reopened in the early 90s. The Lacey V Murrow Bridge had a 62-meter movable span that could retract into a pocket in the center of the bridge that allowed boats to pass. This was one of the earlier floating bridges to be built in Washington state. I think actually being built in 1940 might have been the first, or at least the first major. And so the design, it had some issues. There was a bulge in the bridge deck that required vehicles to swerve across steel joints. And it also wasn't wide enough to accommodate the load at the time, the traffic load in the late 80s, early 90s, when they decided to take on this renovation project. So the bridge had a lane reversal system. So they used X's and arrows and signs to essentially take some of the lanes and make them flow one direction or the other, depending on time of day. So I'm assuming that they're supporting traffic flow in and out of downtown Seattle during rush hour. So in the morning, more lanes are open to traffic into the city, and at night, more traffic is able to flow out of the city.
This seems like it could be a pretty confusing system if you weren't used to it, or even if you were used to it and just not paying attention.
Yeah, because it would change multiple times a day. I'm guessing that the bridge does one thing in the morning, one thing in the afternoon, and then constant the rest of the time. We have a bridge in Calgary, the Lower Center Street Bridge, that I think it's only into downtown in the morning, out of downtown in the afternoon, and during the rest of the day, traffic flows both ways.
And then I believe the upper bridge deck of that bridge, it's 3 lanes into downtown in the morning, and then 3 lanes out of downtown at the end of the day.
Also confusing. I think we mostly have the hang of it by now, but yeah, those lane reversals are not ideal. They built a parallel bridge, the Homer H. Hadley Memorial Bridge. He was the engineer who built the Lacey V Murrow originally. They built that parallel bridge to alleviate the pressure on the Lacey V Murrow and give traffic an alternate option. So those two bridges run in parallel. Nowadays, the Lacey V Murrow carries all eastbound traffic, and the Homer M. Hadley carries all westbound traffic. But when the Hadley Memorial Bridge was first opened, it was used to carry all traffic so that they could shut the Lacey V Murrow and renovate it. So that's when this sinking occurred, was when they had closed the bridge for major renovations. The bridge needed resurfacing and also widening. So as we talked about before, sometimes the bridge deck is wider than the pontoon. So there was a number of pontoons underneath the deck, and then they had these cantilevered sections to make the deck wider than the pontoons, which allowed them to expand the width of the bridge. In order to resurface the deck, they have to remove the original unwanted material, and they decided to do this by hydrodemolition, which is high pressure water. Essentially, they power washed off the topping on the bridge deck. That water was contaminated. They couldn't just dump it back into Lake Washington. They had to dispose of it. And so the engineers on this bridge renovation project analyzed the original pontoons, and they decided that those pontoons were over-designed and they could be used as temporary storage for the contaminated water. They cut holes in the sides of the pontoons. I don't know quite why, but they didn't install watertight doors right away, which to me, that would be kind of step one. Cut hole, install door, and then you can take the door on and off as you need to put the contaminated water in or remove it from site. But for whatever reason, they didn't. I also think it's really interesting because of the contaminated water in the pontoons. The bridge actually sat lower in the water than normal. Let's say under normal circumstances, the bridge deck was 5 feet from the water surface. With the contaminated water in, maybe the bridge deck was 3 feet from the water surface or 2 feet from the water surface. I don't know that number. I'm just giving general numbers for reference, but the bridge sat lower in the water than it had originally had. American Thanksgiving in 1990, so November 23rd to 25th, with those pontoons missing those watertight doors and already being somewhat full of contaminated water, they also took on rain and lake water. On November 24th, the workers noticed that the bridge was starting to sink, and they tried pumping water out of the pontoons, but they were too late. On Sunday, November 25th, 1990, an 850-meter section of the bridge sank and dumped contaminated water and tons of bridge material into the lake. What happened was one pontoon section filled and started to sink, but since the sections were all cabled together, it pulled the rest of the sections down with it. And when this happened, a bunch of cables for the parallel Homer M. Hadley Memorial Bridge, a bunch of those anchor cables were damaged, and it also had to be temporarily closed until they could repair that bridge as well. Even though they had a secondary bridge that was supposed to be handling traffic while the Lacey V Murrow was being repaired, this sinking knocked out both bridges temporarily, and that crossing was closed for a period of time. One thing that I thought was interesting, in addition to them not not installing the watertight doors as soon as they cut the holes in the pontoon, was that the hydro demolition took place in September, and this didn't happen until November. And so they had, in my mind, plenty of time to remove that contaminated water before this occurred. And, again, hindsight's 2020, but I don't know why they didn't do that. I don't know why they didn't install the watertight doors. I don't know why they didn't remove the water. Like, it seems like this bridge sinking, this failure was completely avoidable. I mean, all of the ones I've talked about so far are, but this one especially so.
This seems very avoidable, with 6 to 8 weeks for not installing watertight doors, and then having the water in the pontoons just sitting there instead of maybe pumping it out once a day or every 3 days or every once a week. Some period of time where the bridge would still be able to float. They would still be able to deal with the contaminated water at an off-site storage facility or off-site processing place. This seems like a very avoidable sinking of a bridge that should have been floating.
Yeah, so I will say it's not a scenario where we have 10 pontoons. I mean, there's probably hundreds of pontoons under that bridge. So, it is a big undertaking to install those doors, but to me, cutting the holes and installing the watertight door is step one. And then you remove the doors as you need to put in or take out the contaminated water. Again, hindsight's 2020.
Or even have a connection valve of some sort, where if you have hoses or however they were going to do this, there seems like a better system than just watertight doors that didn't get installed.
Yeah, I don't know. The Hood Canal Bridge, I mean, that one sunk in 1979. Maybe that one wasn't as obvious, but this one occurred 11 years later. You'd think that Hood Canal sinking would still be fresh in everyone's mind, and they would have been all that much more aware of what the risk would be, and they would have taken the steps to mitigate that risk. It seems weird to me that they didn't. And I don't really know why.
Yeah, like a lot of the engineering work that we do, risk mitigation plays a huge factor in execution plans and engineering design. So the fact that they didn't fully consider a lot of potential risk in this is a little troubling. However, out of this, the state of Washington convened a governor's blue ribbon panel to make some recommendations about floating bridges. Some of the recommendations from the panel included electric monitoring of water levels in the pontoons, severe weather planning being a necessity, continued flotation during construction is imperative.
Which seems pretty straightforward to me. Floating bridge needs to stay floating. That's priority one.
During construction, during use, it should remain floating. It's in the name. It's a floating bridge.
Right.
So when they were building these bridges, they'd adopted a standard highway approach that didn't consider a lot of the marine requirements and the vulnerability of sinking for these floating bridges during construction.
Yeah, it sounds like they treated this almost like replacement of a highway on land or a cantilevered bridge deck, where your structure is almost solid and you're just replacing the surface. But with this floating bridge, there's so many other components that I just think they didn't really take into account.
Yeah, so as a result of the governor's panel, this was something that needed to be taken into consideration moving forward. Also, they wanted a third party to review ongoing operations, maintenance, and emergency preparedness. And they also wanted marine contractors involved in the bridge reconstruction or major maintenance projects instead of just highway contractors. So all of these things seem like excellent recommendations and almost things that should have been from the start. However, hindsight is 2020, and going forward, some of these recommendations did likely prevent another bridge from sinking.
Yeah, so that bridge is the Evergreen Point Floating Bridge, formerly called Governor Albert D. Rossellini Bridge. Now, this bridge is a 10-minute drive from the Lacey V Murrow and 90 minutes from the Hood Canal Bridge. So all of these bridges are very close together. The Evergreen Point Floating Bridge is the longest floating bridge in the world at just over 2,300 meters of floating span, and it opened August 28, 1963. It passes over Lake Washington, which is similar to the Lacey V Murrow, and is part of State Route 520. It didn't sink, luckily, but after the Hood Canal and Lacey V Murrow bridges did, the state commissioned a study on the Evergreen Point Floating Bridge. And from that study, they discovered that the bridge would likely only last until 2017. It had to be closed during high winds. Even though it had a seismic retrofit in 1999, it was still at risk of collapse during an earthquake because, as we know, Washington State, as well as parts of BC, Oregon, and California are on a major fault line. And the bridge sat 30 centimeters lower over the water than what it did when it was originally built. And lastly, vibrations from storm surges and strong winds could compromise the drawspan, anchor cables, and pontoons. They ultimately decided that the bridge needed to be rebuilt, or at least a major reconstruction. And so that's what they decided to do. They rebuilt the bridge. It was replaced in 2016. And the state of Washington released a report on this replacement project, and they actually included the construction method. I think that ties nicely with the factors that need to be considered when building a floating bridge that I talked about earlier. So I just want to talk quickly about the construction method of this Evergreen Point Floating Bridge replacement. The first step that they do is they build the pontoons, anchors, and roadway sections elsewhere. They build those off-site. Eventually, they tow them or bring them to site to the final bridge location. Then they drive temporary piles into the lakebed or the riverbed to hold the first pontoon in place, which is interesting. I think I had this image in my head that they tow the pontoons like little ducks in a row and they just kind of tow it into place and off you go. And that's not quite the case, especially the bridge. I mean, it's 2 kilometers long. I don't know why I thought that, but they bring a few pontoons at a time and they build the bridge in place. So these temporary piles hold that first section in place, and then they build from there so that first pontoon isn't moving around. It's kind of a fixed piece, and then it allows them a lot more stability to build the bridge.
That makes quite a bit of sense.
Yeah, not like my concept. I've never built a floating bridge. It's not like I know. You don't know until you read these things.
Well, now you can have all your pontoons in a row.
Exactly. Then they install the anchors to hold the bridge in place. They bring the pontoons, they tow those to the bridge location. Next, they construct the bridge piers. So the approaches to the bridge, the on and off ramps that allow you to get onto the floating section, those have fixed piers. I think as a minimum, you'd have one fixed pier per side, but some of them, especially like the one in Kelowna that has the larger section for water traffic to pass below, that probably has several piers. They install what they call a cross pontoon at the temporary piles. So that pontoon is perpendicular to the bridge orientation. That cross pontoon acts as the edge of the floating section. And so there's one of those on each end of the floating bridge. And then from that cross pontoon out, they assemble the different sections of pontoons. And then they build what they call the superstructure or the bridge deck on top of it. And they just repeat that process until they get all the way across the water. Because the original bridge was left in place, functional, still operating while this replacement was being built. The replacement was built slightly off of where its final location would be, so it's slightly further downstream or perhaps upstream from its final location. So once they got everything together, then they shifted it into place. And I think they just did that so that they had more access to all sides of the bridge. It would be really, really difficult to build the bridge in place when there's a second bridge right next to it, has fully flowing traffic, because if you need to access that side, now you're either doing it over top of traffic, which is silly, or you only have access to one side of the bridge. So that's why they did that. I think if it was a new bridge that they were building from scratch, they would probably build it in place, but that was not the case here. Yeah, so that's how they build floating bridges. These are really interesting projects. I've never built a bridge before, but I do find them really interesting. I like tunnels as well. I don't know if it's maybe the waterway crossing piece that gets me, but I do find these bridges really interesting. I learned a lot reading about this researching this episode.
So there you have it. 2 floating bridges in Washington State that didn't remain floating. Risk mitigation is an important part of every engineering design and project, and it may not have been adequate for the Hood Canal Bridge and the Lacey V Murrow Bridge. However, from the recommendations of the Governor's Blue Ribbon Panel that was convened after the first 2 bridges sank, a 3rd bridge was likely spared from sinking, and appropriate mitigations, as well as a new bridge, were put into place.
For photos, sources, and transcripts from this week's episode, head to failureology.ca. If you're enjoying what you're hearing, please rate, review, and subscribe to Failureology so more people can find it. If you want to chat with us, our Twitter handle is @Failureology. You can email us at thefailureologypodcast@gmail.com, or you can connect with us on LinkedIn. Check out the show notes for links to all of these. Thanks everyone for listening, and tune into the next episode of Failurology, where Brian and I will talk about the Kursk, the Russian submarine that sank. Yes, like bridges, submarines can sink too. But more on that next time. Bye everyone. Talk soon.